This is a recording for 7.4 notes in pre-calculus, and this is part 2. We were in the midst of this problem, and we had just decided that we were going to multiply all of the terms by the common denominator to get rid of the fractions. So when we do that, we're going to multiply this by x times x plus 1 in parentheses squared for each term. And on the left, the denominators just cancel. On the right, the x's cancel in the first one. Since it's x plus 1 in parentheses squared on the top and just x plus 1 on the bottom, just the x plus 1 cancels with the square on that one. And then the x plus 1 in parentheses squared cancels on that third one. So then when we rewrite this, we get 5x squared plus 20x plus 6 equals a times parentheses x plus 1 in parentheses squared plus b times x plus 1 plus cx. So if you remember our next step, this is where we pick convenient values for x, and that's not always going to work for us, but I think we can make it work at least to begin with here. So I'll write myself a note, pick convenient values for x. And so I'm going to let x equal -1. That'll be my first one. And I just put that in for both sides of the equation, see what happens. So if you want to pause this and try that, go ahead. And that should allow you to find c, I think, because the a term is going to drop out, and see what you get. So when we pick our convenient values, oh, maybe I already showed part of that, and we let x equal -1. When we solve that, we get -9 equals -c, so c equals 9. And then our other convenient value to pick is x equals 0. If you haven't already done that, go ahead and try letting x equal 0, so some of those variables drop out, and see what you get. Then for that one, we should have let x equal 0, and we get 6 equals a. So those two are pretty straightforward. Now, that seems like all of the kind of easy to pick values. So there's no other easy to pick value, but now I know what a and c are, so I can just pick, generally I pick a small number to let x equal something, and I use my a and c as well, and then that will allow me to find b. So I'll write myself a little note about that as well. There is no easy other value for x. So I just have to choose a value of x. And, I just want to be not crazy. I wouldn't pick, 864 or -236.4. I want to pick kind of easy things that I haven't picked already. So I picked x equals -1, x equals 0. So I'm just going to let x equal 1. So I'm going to pick x equals 1, and so that I only have one variable in there, I'm going to remember, and I'm going to use the fact that a equals 6 and c equals 9. So go ahead, put in 1, 6, and 9, and see if you can find what b is. So let's see how that went. When I put that in, I put in 1, I get 5 plus 20 plus 6 equals 24 plus 2b plus 9. That gives me 31 equals 33 plus 2b. That gives me -2 equals 2b, and then b equals -1. So now I have my a, b, and c values. And so now I can kind of go all the way back to the top here. And I'm going to just write in yellow for a minute. So that is all of this, which is the equivalent to this piece. But remember, we started out with this whole thing, and it was equal to this. And now we're going to replace that piece of it with all of this, and then we're going to put A, B, and C in for that. And so I don't have room right here, but I'm gonna kind of transfer a bunch of that down to the very bottom. So from above, we know that big improper fraction, x to the fourth plus 2x to the third plus 6x squared plus 20x plus 6 over x to the third plus 2x squared plus x is equal to x plus that big fraction that we just decomposed. And then that fraction part, we have to keep that x, and maybe you can tell it's a little thicker. I added it back in, plus x plus a over x plus b over x plus 1 plus c over x plus 1 in parentheses squared. And then substituting in my values, I get that this big fraction here, and maybe I can clone that, is equal to x plus 6 over x plus negative 1 over x plus 1 plus 9 over x plus 1 in parentheses squared. Now, as we move on, we're going to look, we've had only linear factors as we've looked at that. We had, and then we have repeated linear factors in this last one. Now, before we kind of write the rule, we also want to investigate what happens if they're not all linear. So moving on, and this is the next thing we want to look at. Let's see, the procedure used to solve for constants works well when the factors are linear. However, if the denominator includes, and maybe I'm going to underline this, when the denominator contains irreducible quadratic factors, then we are going to use a different procedure, and that involves writing the right side of the basic equation in polynomial form, equating the coefficients of like terms, and using a system of equations to solve for coefficients. So you might want to write yourself a note, maybe even about the fact that number 1 and number 2 used linear factors. And hopefully you were kind of getting that process in your head a little bit. And now, starting with number 3, we're going to have quadratic factors as well, maybe linear factors also, but adding in quadratic. And we're going to use kind of a different procedure. So at this moment, just kind of give yourself a little heads up that this is going to be maybe a different procedure as we go through. So here's problem number 3. And this is to write the partial fraction decomposition of 3x squared plus 4x plus 4 all over x to the third plus 4x. And after we do this one, we'll write ourselves that algorithm of how to do this. So think about your first step. It's the first step all the time. We're going to factor the denominator. So factor the denominator. And notice it's x to the third plus 4x, so it has a common factor of x. So x, when we pull that out, we get x squared plus 4. Now, if that was x squared minus 4, we'd factor it into x plus 2 and x minus 2. But if you think about trying to set that equal to 0, I get x squared equals negative 4, x equals plus or minus the square root of negative 4, so that is irrational. Or excuse me, imaginary. It would be plus or minus 2i. So we can't factor that any further. So we still have, and these are just two factors, this one and this one. This is considered linear, and this is an irreducible quadratic. So when I write my fractions, I'm going to have just this factor as one denominator and then this factor as the other denominator. So I'm just going to have two fractions there. And I'm going to get rid of all that yellow. And I just wanted to think about that as we go. So when I write this, it's equal to, and I'm just writing my denominators to start with, something over x plus something over x squared plus 4. And then I'm going to go back to yellow a minute and I'll get rid of it. So remember on the denominator here, that's x to the 1. So we need a constant here. So that's just going to be a number. But this is x squared. And so we just want one power lower. So we want something x to the first. And then, we could still have a number there as well. And so the way that we're going to do that, and I just keep using capital letters A, B, C, D, E, F. And the book authors, when they talk about it in the algorithm that you'll see after this problem, they subscript all these things. And to me, that's just like too much of a mess in practice. That's a good for our rule, just to know what's happening. So this time, our numerators are going to be a over x, because that's linear, so we just put a constant, and then plus, this one has a quadratic on the bottom, so it's going to have a linear factor on top, bx plus c. And this only works when we are having an irreducible quadratic. So don't just think, oh, I'll just leave it as a quadratic and write it this way. Please don't do that, because we want it to be the basic factors as we go through that. So now try to remember what we do next. We write this and then multiply everything by the least common denominator. So we're going to take each term and multiply by x times x squared plus 4. And when we do that, we can do a bunch of canceling. And then I'm just going to write what that is equal to. I have 3x squared plus 4x plus 4 equals a times parentheses x squared plus 4 plus bx plus c times x. Now, I'm going to write in yellow again so I can kind of think this through. So I have something x squared plus something x plus my constant number. And I want to end up with something x squared here plus something x here plus something. And then what I'm going to do is I'm going to match this coefficient of x squared with that coefficient of x squared, and I'll solve for those, and then I'm going to multiply the coefficient, set this coefficient of x equal to that coefficient of x, and I'm going to have another, I said I was going to solve for those. I mean, that's going to give me one equation, then this will give me another one, and then I'm going to take the constant stuff equal to the constant stuff, and then that's going to give me 3 sets of equations, and I have 3 unknowns, A, B, and C. So I'll have 3 equations and 3 unknowns, and I can go through that process that we just learned how to do, solving systems of equations that have more than 2 variables. So that's how we're going to approach this. And don't be intimidated by this, because I think you're going to find, at least in this one, that our system of equations is going to be super easy to solve. And we may not even put it in row echelon form. We might just kind of solve it. But first, we're going to do things a little differently, and we're just going to manipulate this right-hand side so that we get it in the form of something x squared plus something x plus our constant. And so let's just kind of do that right now. And when I do that, I'm going to get, first I'll just distribute. I'll get ax squared plus 4a plus bx squared plus cx, distributing that x from the bottom back, excuse me. And so this is a x squared plus bx squared plus cx plus 4a. And then I'm going to factor out the x squared, so I just kind of know exactly what that is. And that's going to be a plus b in parentheses times x squared plus cx plus 4a. And those could be more involved. In this one, they're not super involved. I'm just going to move the left side down. So 3x squared plus 4x plus 4 is my, my situation right now. Again, I need to figure out what A, B, and C are. That's my kind of job right now. So now I'm going to do this matching game. So on the left, my coefficient of x squared is 3. On the right, it's a plus b. So 3 is equal to a plus b. And then the next one, the coefficient of x here is 4, and the coefficient of x there is c. So I'm going to write 4 equals c. And my last one is going to be 4 again, and that's my constant equals 4a. So 4a equals 4. Now, that's my system, and I might, at least write it a little bit differently before I solve it. I like to have my constants over on the other side. So I'm going to write a plus b equals 3. I'm just going to keep it as c equals 4 and 4a equals 4. To me, I don't think I want to even put this in row echelon form because it's pretty straightforward. I can just start solving right away. And so I'm going to say that since 4a equals 4, a equals 1. I'm told that c equals 4, so that's done. I know a plus b equals 3, and a was 1 plus b equals 3, so b equals 2. So I have that, and I'm just going to write them over here. A equals 1, b equals 2, and c equals 4. So now I have what I need, and I'm going to go way up here, and I'm gonna re-find that long version. Maybe I saved it. Let me see. No, I did not. I thought I saved it, but I'll bring it down here, and we'll see what that looks like. Oh, and I didn't even comment on the fact that this is a proper fraction, so I didn't have to do that initial division as I went through this. And so now this means that 3x squared plus 4x plus 4 all over x to the third plus 4x becomes, as a decomposition, 1 over x plus 2x plus 4 over x squared plus 4. And that is the partial fraction decomposition. Now that we've done a few of these, let's look at that algorithm or rule and take some good notes on that. Now we're going to write our how-to. And I'm going to just make this a little bit bigger so it's easier to see for you. So take some time. I will read through this, and this is the directions. This is the decomposition of n of x over d of x, so numerator denominator, into partial fractions. So number 1, divide when improper. So remember, I think that was our second equation. When n of x over d of x is an improper fraction, degree of the numerator is greater than or equal to the degree of the denominator. Divide the denominator into the numerator to obtain n of x divided by d of x equals a polynomial plus n of x, n sub 1 over x over d of x. So we did that. Then you apply steps 2, 3, and 4 below to the proper rational expression. So just to the fraction part, which is this, n sub 1 of x over d of x. Note that n sub 1 of x is the remainder from that division. But, you know, it could be our original problem if it's already a proper fraction. Then we're going to factor the denominator, right? We did that a bunch of times. Completely factor the denominator into linear and quadratic factors, where the quadratic ones are irreducible. Then for the linear factors, for each linear factor, you are including the sums. And so for the linear factor, you have to have it to the first, to the second, up to however high of power it is. And we had that, I think that was also in the second problem, where we had x plus 1 maybe, or x minus 1 in parentheses squared. And on top of those, you just put a constant. We just call it ABC. And then the quadratic factors, which aren't reducible, we write those, and we write something x plus a number, a linear factor on top of that. So let me go up to the beginning here. I'm going to have you pause this, and then I'll slide it down a little bit, and you can pause it again. Now, let's move on and try another one of these. So here's our next one. You let me know if you want to try this, or try parts of this, or what you want to do. And otherwise, I'm just going to kind of start working through the problem. So this is for write the partial fraction decomposition of x to the third, 8x to the third, plus 13x all over x squared plus 2 in parentheses squared. And so for this one, we're going to do, our first job is to factor the denominator. And what do you notice? Well, it's x squared plus 2 in parentheses squared. Well, x squared plus 2, that is quadratic, but it's irreducible. But it's also squared. So when we write our partial fraction decomposition, we have to have an x squared plus 2 as one of those to the first power, and then we have to have another denominator that's x squared plus 2 in parentheses to the second power. So that's a little tricky thing too. Every factor, we have to have it from represented as a denominator for every power up to the power that it's given at. Now, those are both quadratics, so we have to call our numerators ax plus b and dx plus c as we go. And then we're going to do that multiplying by the common denominator to get rid of the fractions. So as I move along, I just noticed that I wrote that as dx plus c, and I meant to write it as cx plus d. So go ahead and change that. I'll change it in a moment. I already did some more work, so I have to kind of show that work. When we multiply both sides by x squared plus 2 in parentheses squared, we can cancel a bunch of things, and in this one, notice that, you know, that whole denominator canceled on that very right one. And we get 8x cubed plus 13x equals ax plus b times x squared plus 2 plus, and that's where I kind of realized I didn't have it as cx plus d, plus cx plus d. And I thought about writing it as times 1, but we don't really need that. So now what are we going to do? We're going to do that same thing we did in the previous problem when we have these quadratics. And I'm just going to kind of remind you that really we want our 0 placeholders. So I'm writing in yellow right now, but I have something x to the third. Let me just kind of make it something x to the third, and I want to kind of have a 0 x squared plus something x plus just a number constant, and then I want to get the same kind of thing over here, something x to the third plus something x to the second plus something x plus some number and just kind of see what happens so that I can kind of match those parts. So on the left, I am just going to rewrite that with 0 placeholders, but maybe I'll wait until I clean up the right. So I do have to distribute this. So ax times x squared is ax to the third. Plus ax times 2 is 2ax. Plus b times x squared is plus bx squared, plus 2b, and then plus cx plus d. And so now I just want to take this right-hand side and just have it in decreasing powers of x. So I have ax to the third plus bx squared plus 2ax plus cx plus 2b plus d. And then I'm gonna, well, probably maybe put that in parentheses just to show that that's my constant and distribute out that x. So I have ax to the third plus bx squared plus parentheses 2a plus c x plus, and I'm just putting that in parentheses for convenience, 2b plus c in parentheses. Then on the left now, I'm going to write that from x to the third down to 0 using placeholders for everything. So I have 8x to the third plus 0x squared plus 13x plus 0. And so that's my kind of left-hand side and my right-hand side. Now, I'm going to make a system of equations again. I'm going to match the cubes, the squares, the linears, and the constants. And I'm going to get, I have 4 unknowns. I'm going to get 4 equations and 4 unknowns as we look at that. And then I'll maybe put it either in row echelon form or something similar, because you're going to find for at least these that we're working on, if they did turn out to be, you know, that big row echelon, big equations, we maybe involved equations, we maybe would want to put it in row echelon form. But let's just match those and see what we get. So I get, and I'm going to put the variable first and the constant second. So this is going to be my system. And I'm going to have 4 equations, 4 unknowns. So the first equation, A, and I'm going to skip over here to 8. So I have room to write my other ones. The next one has 0, and that's B. So I'll go in a little bit. B equals 0. Kind of, it's almost falling into row echelon form if I want to think of it that way. The next one, 13, matches this. So 2A plus C. Put that a little closer. Equals 13. And our last one is 0 and 2b plus c. So 2b plus, excuse me, I apologize because I lost my D. I don't know how I can do this because I do have my notes in front of me, but I somehow don't write them down correctly. That was a D the whole time, and I somehow made it into a C. And I think everything else is right. Now let me just kind of pause myself and check that. Yes, it is. And I usually do eventually find my mistakes. So plus D equals 0 for this one. Now, you know, do I have to get that in row echelon form? In this situation, I feel like, you know, I think I have enough information to solve that without putting it in row echelon form. And they didn't tell me to do that. So, you know, in that last section, we really focused on that row echelon form. Now it's just, you know, use whatever method you can to find what these are equal to. And so I'm just going to start writing them. I know A is 8. I know B is 0. I know 2A plus C is 13. And since A is 8, 2 times 8 plus C is 13. So that's 16, and 13 minus 16, C is negative 3. And then for D, oh, excuse me, 2B plus D equals 0, and that is going to be 2 times 0 plus D equals 0. So D equals 0. And just note to self, and that didn't look like a D very well. Note to self, you could even have a fraction where it does not, there's no numerator, the numerator is 0, so then you just get rid of that one. But that won't be the case here. So here's my original, and so that means then that this whole thing is equal to 8 over x plus, oh, just a second, that's not the right problem. I thought I had saved that. Let me get rid of that. So now we have 8x to the third plus 13x all over parentheses x squared plus 2 in parentheses squared is equal to 8x plus 0, so we're not going to write that, over x squared plus 2 plus negative 3x plus 0 again, so we're not going to write that, over parentheses x squared plus 2 in parentheses squared. And so that concludes problem number 4. And that concludes section, or excuse me, part 2 of section 7.4.